All right, so today we're going to be talking about symmetry. These notes were provided for you, so you're looking for the packet that says Symmetry Notes. So we can talk about symmetry. So there's a variety of different types of symmetry, and the first one we're going to talk about here is point symmetry. And what it means is an object is symmetric to a single point. An easy way to identify it is if you can rotate it 180 degrees and it looks exactly the same, then it has rotational symmetry, or point symmetry. The second type of symmetry would be line symmetry. And line symmetry is essentially if you can fold it on itself and it matches up, then it has line symmetry. All right, so some examples of shapes. So something that has line symmetry but not point symmetry. So if you think about, there's lots of different shapes that have this, but an easy example are capital letters. So like if I did the capital letter A, I could fold it on itself and there would be a line, but if I flip it upside down, it is not going to be the same. Maybe the letter C. Okay, I can draw a line down here and it's going to match, but if I flip it upside down, it's going to be facing the wrong way. One more, maybe a capital B. Point symmetry, but not line symmetry. And this is a little bit harder to picture, but if we use the letter S. So let me use this to illustrate point symmetry. There is a point on this object that every point on one side of that dot has a counterpoint. So those, here to here, here to here, but there's no line that you can fold it on that it's going to end up on itself. A capital letter Z. There would be a point in here. Also, if you turn it upside down, it still looks like an S and a Z. And once you think of Z, you can start thinking of other ones like N. Okay. Now, coming up with things that have both line and point, that's pretty easy. Always everybody goes, well, letter O. Yep. There's a line of symmetry there, there's a line of symmetry there. If you turn it upside down, it's going to look the same. Capital letter H. And maybe an X. All right, so we're going to do an example here. If P is at -2, 2, so we'll go ahead and plot that point. There's P. We're going to find the coordinates of a point P prime if P and P prime are symmetric to the origin. So here's the origin. An easy way to do this is to stair step it. So if I go from here to the origin, I'm going over 2, down 2. I'd repeat that, over 2, down 2, and then those are now symmetric to the origin. The second example here says if P and P prime are symmetric to the point 1, 1. So here's 1, 1, call that M. And I want this one to be symmetric to this point. So again, I'm going to go over 3 this time and down 1. So I'll repeat that, over 3 and down 1. And now those 2 points are symmetric to that dot. Now usually in class at this point I hand you something called a mirror and we investigate some reflections using those. But we don't get to do that this year and that's okay. But we're going to take this curve and I'm going to essentially reflect it over all of these lines. Okay, so I'm going to take this and reflect it over the x-axis. So every point is going to get drug across the x-axis. So this point's going to be here, this one's up 2, so it's going to be down 2. This one's up 3, so it's going to be down 3. Okay, so that one's our x-axis. Okay. Now the y-axis. So this is our y-axis. and I'm going to reflect this over here. So any point that's going to get drug across, that's drug across. Okay, so this would be the y-axis. Okay, the next one is the line y equals x. So we're going to draw the line y equals x. Which is this line here. Okay, so this one is going to get reflected over that line. So if you picture folding this, this is now going to be up here. So this point is actually going to end up on itself. And then this one is going to get reflected over here. This one is going to get reflected over here. So it's just going to this line and straight across. Okay, and then the last one we're going to do is, well, not the last one, y equals negative x, which is the other diagonal. So here, we're going to fold it over this line. So it's going to start here. This point is going to get drug across over here. This one over here. So it's going to end up being like that. Okay, and then lastly, we're going to do the origin. Okay, so the origin, we're going through a single point. So this point is going to be here. This point over 4 down 2 is going to be over 4 down 2. This point here is over, we're going over 9 down 3, so we're going over 9 and down 3. So in the origin is actually the same as a 180-degree rotation. All right, next we're going to do all of that same thing with a single point. So we're going to take the point 4, 2, and we're going to do these 4 or 5 different reflections. So we're going to take this over the x-axis. Okay, and then we're going to look at the coordinates. So the coordinates here are 4, negative 2. Okay, we're going to take it over the y-axis. So we're going to pull it over here. Okay, and its coordinates are negative 4, 2. Okay, we're going to take it over the line y equals x. So let's go ahead and draw my line, and then we're going to go straight to this line and straight across. Okay, so if we look at the coordinates there, we're at 2, 4. And if we look at y equals negative x, so just draw part of that line. Okay, this point, we're going to go straight to that line. So we went across 3 diagonals, and we're going to go 3 diagonals here. So that's a negative 2, negative 4. And then the origin, we're going over 4 down 2, so we're going to go over 4 down 2. So here this is going to be negative 4, negative 2. So from this we can come up with some patterns, some rules for if we take a point and it's symmetric to the x-axis or y-axis. There's a pattern there. So I'm going to use what happened with the point 4, 2 to generalize it to just a generic point AB. So 4, 2 went to 4, negative 2, which means AB is going to go to A, negative B. 4, 2 went to negative 4, 2, so that's a negative A, B. 4, 2 went to 2, 4, so if I have AB, that's going to be B, A. For y equals negative x, we started with 4, 2 and ended up with a negative 2, negative 4. So it's going to be a negative B, negative A, because it's basically this one, but negative. And then the origin, okay, went 4, 2, negative 4, negative 2. So origin here is going to be negative A, negative B. Now, without having to graph the point, we can come up with the coordinates for the same symmetries. So we're just going to apply these rules, and negative means opposite. So if we're going to take 3, negative 4, and apply this rule, the 3 stays the same, but the negative 4 becomes opposite. So it's going to be positive 4. Y-axis, we're going negative A, B, so that's going to be a negative 3, negative 4. Y equals x, they switch places. So this will be negative 4, 3. Y equals negative x, we're going to take them, switch them, and make them opposite. So that will be 4, negative 3. And finally, the origin, they just both become opposite. So that's going to be negative 3, positive 4. Okay, now we're going to take this little graph, this arrow, and we're going to graph it again with the same symmetry. So if it's symmetric to the x-axis, we're going to have an arrow going down. If we're symmetric to the y-axis, this guy gets reflected over here. The line y equals x, so it would be this line here, it switches the x and y's. So instead of having a point at 2, 0, we're going to have a point at 0, 2. Instead of having a point at 2, 2, we're going to have a point at 2, 2. So the arrow goes this direction. And then for y equals negative x, okay, if you think about it numerically, we're taking this one and making them all the opposites. So instead of 0, 2, we'd be at 0, negative 2. Instead of being at 2, 2, we'd be at negative 2, 2. So it's like that. But again, if you draw that line y equals negative x, this arrow will get reflected over there. So another thing we can do is determine if an equation, so for example, y squared plus x squared plus 1, if it has any particular symmetries, and we would do that by plugging in a test point. Now these test points match the symmetry rules. Okay, if you plug it in and it remains exactly the same, then it has that symmetry. If it changes, then it's not the same. So for example, this one, when we plug in x negative y into this, negative y goes in here, x goes in here, and it stays the same. Here, y goes here, negative x plugs in there, and simplifies down to the same. Same there. Here, however, when I put whatever goes in the first spot replaces the x. So the x gets replaced with the y, and the y gets replaced with the x. And this is not the same. So this is not symmetric to the line y equals x or the line y equals negative x. Okay, so let's do another practice. So we're going to substitute in to see if this has any of these symmetries. So my first one, we're going to take the y and replace it with negative y. X stays the same. So we'll get y squared equals x cubed, which is good. here. The y is y. The x is a negative x. A negative x cubed is negative x cubed. Negative y squared equals negative x cubed. Not the same. If I switch their positions, x squared equals y cubed. Oh, and it's definitely not going to work when we switch it again. So this is going to be a negative x squared equals a negative y cubed, which is x squared equals y, negative y cubed. Not the same. So it's just a quick way to check it if you would like. So one of the major applications of symmetry is going to be defining functions as an even function or an odd function. So we're going to first define this graphically. So if you have a function that is even, then it is symmetric to the y-axis. So something like a parabola, if I fold it the y-axis, it's going to be symmetric. So this would be an even function. Okay, that graph, if I folded it, would be symmetric to the y-axis. Odd function is going to be symmetric to the origin. So something like that. So if you can flip the graph upside down and it looks exactly the same, then it is an odd function. Okay. So a lot of people say, well, if this is y-axis, then this should be x-axis. But if something's symmetric to the x-axis, it is not a function. Okay, so if the point 2, 3 is on the graph, what other point must be on the graph if the function is even versus odd? So sometimes it's helpful just to sketch yourself a little picture. So the point 2, negative 3 would be down here. Well, if it's even, then there's a point on the opposite side of the y-axis. So it would be at negative 2, negative 3. My 2, negative 3 here. If it's odd, then I have it over here. So if this is 2, negative 3, this would be negative 2, positive 3. So we're going to use the graphic definition to complete the graph. So if it's even, that means it's symmetric to the y-axis. So it would look like that. If it's odd, if I flipped it upside down, it's going to look the same. So it's going to look like that. Graphically, an even function is symmetric to the y-axis, but the formal definition is actually an algebraic one. So I'm going to draw a sample even function. Okay, this is even, it's symmetric to the y-axis, and I'm going to pick a test point. This point here, we're going to call x, and then that's whatever we get if we plug it in, so f of x. So this point is x, f of x. There's a counterpoint over here, because there's always a point on the other side of the y-axis, that if this is x, this distance would be negative x, but this is exactly the same, so negative x, f of x. So the algebraic definition of an even function is that if I evaluate f of x, it will be equal to what I get when I evaluate negative f of x. So that means f of negative x is equal to f of x. Think about that numerically. That means 2 and negative 2 are going to have the same y value. 10 and negative 10 are going to have the same y value. That f of a negative will be equal to its counterpart. Versus an odd function, which would be symmetric to the origin. Okay, I'll pretend that's symmetric. So I'm still going to use that same x, f of x. And there is a counterpoint on the opposite side, where if this is x, this is negative x, but rather than it being equal, like on an even function, it's actually going to be opposite. So when I evaluate the function at a negative x, it is related to what it is on the positive side, but it's always going to be opposite. So f of negative x is equal to the opposite of whatever f of x was. So without the graph, we're going to use f of negative x, and if f of negative x equals f of x, then it's going to be even. And if f of x, negative x, equals the exact opposite, then it's going to be odd. And if it's somewhere in between, then it's neither. Okay, so I have some equations here. I'm going to give myself a comparison. So this is y, or f of x, those would be equivalent. So the opposite of that function would be a negative x squared minus 8. Okay, so that's just giving me a comparison. Now I'm going to actually plug the value in. So I'm going to say f of negative x. That means anywhere I see an x, I'm going to replace it with a negative x. Simplify it. So that will be x squared plus 8, which means f of negative x equals the original equation. It did not change. So this one is even. Negative, the opposite function here would be negative x cubed minus 4x. Then we'll do the test. So this is just a comparison, and if you don't want to do that part, that's fine. So f of negative x, pretend that's a negative x, equals negative x cubed plus 4 times negative x. Okay, simplify that. We're going to have negative x cubed minus 4x. Well, that and that are the same. So we're saying f of negative x, when I evaluated the function at negative x, I got exactly the opposite, which makes this odd. Next one, so the opposite would be 3x squared minus x plus 2. Okay, so we'll plug in our negative x. So this becomes negative 3x squared, because that just becomes positive. This will be negative x, and that'll be minus 2. Well, that is opposite, or that stays the same. That one became opposite, that one stayed the same. So this would be neither. And if you think about it, there are a lot of graphs that don't have any symmetries. They're not symmetric to the y-axis. They're not symmetric to the origin. Okay, this one's a little bit tricky because we're dealing with a fraction. Okay, so I'm actually going to do the evaluation, and then we'll go from here. So here, f of negative x, on top we'll have negative x cubed minus a negative x. On the bottom, negative x squared plus 1. So we get negative x cubed plus x over x squared plus 1. So if we look, the top is the exact opposite. The bottom is exactly the same. And fractions are going to behave a little bit differently. Okay, so I want you to think about a fraction. If I had 2/3, the opposite of this would be negative 2/3, right? Well, To arrive at this, we can make this a -2/3, which would be equal to this, which would be opposite to this, or it could be 2/3. So if one part of the fraction is exactly opposite, that means the whole thing is opposite. Now, if we had gotten opposite over opposite, well, that would be exactly the same. So if everything changed on the top and the bottom, then it would actually be even. But this one is going to be equal to the opposite, because this is basically a negative over a positive, which means it's opposite. So this is going to be odd. Last one is tangent. Now this one I'm going to do a graphic approach. So the graph of tangent. Okay, and you can graph it on your calculator if you're not sure. Okay, and you're looking for the symmetry. So if I took this and I rotated it 180 degrees, it's going to look the same. So this one is odd. So you can use the calculator to help you out with some of those decisions, but that is all about symmetry.